All right, here I'd like to get into giving an example of using the first derivative test and the second derivative test to determine local extrema. That's the goal of the two tests, really. You can use it for a variety of things, but in the definitions, it's got to do with determining local extrema. So what I'd like to do is give an example here. Let's go over to my iPad and go to a problem that had been given in the text. Just if you saw the last section, they use this as an example of where it's concave up and concave down and point inflection points, etc. But let's do this problem now from the beginning and use the first derivative test and the second derivative test to do some calculation. So the first derivative test, let's do that first. Right, so f prime, first of all, let's look at what does the graph look like. Get that in your head, all right? So it's a cubic function. X cubed starts bottom left, goes top right, but it's got some stuff in between here. Therefore, it's gonna look something like this. Down to the left, up to the right, and probably a peak and a valley in the process of getting through it, all right? So we've got a max, we're gonna have a local max, and we're gonna have a local min that are occurring in that order. So we can know that that's coming. Get a picture of that. Okay. If it was negative x cubed, then it would be reversed. You know, we can have a picture. The min would be on the left and the max would be on the right. But this is what we're working with. So now we're going to take the derivative of this function and get 3x squared minus 12x plus 9. All right. We'll stay with this. In a minute, I'll rewrite that again and start over when we're going for the second derivative. You could just take the second derivative right now. I wanted to keep it together where we're doing the factoring right underneath it and work with it in this sort of fashion. So what I want to do right now is I'm going to set this equal to 0. Well, let's factor it first. 3 is common. X squared minus 4x plus 3. And that then factors down to x, 3, and 1. It's got to be. And it's negative in between, so they both have to be negative. All right? Now we set that equal to 0 and determine the critical points. So x minus 1 equals 0 and x minus 3 equals 0. X equals 1, x equals 3. Those are our two critical points. All right, and notice there over on the number line that 1 is to the left and 3. I don't have the y value here, but I know that 1 is going to be the max because I hit that first as you come from the left. And then 3 is going to be the min. I'm going to see that, okay? So, but for right now, I'm just using the first derivative test to verify the situation. First derivative test, I need to check the slope to the left and to the right of each critical value. Right? Each critical number. So I'm going to pick values. 1 to the left of 1, easiest, 0 is going to be right here, so I'll pick 0 as 1. 2 is in between 1 and 2, so I'll pick 2. And to the right of, keeping an integer that's positive, you know, I'll just say the smallest one is at 4. So I'll pick the values 0, 2, and 4, and I need to determine the slope of those, the slope of the function at each of these 3 points. So I need f prime at 0, f prime at 2, and f prime at 4. Give yourself a little room when you do these. Make sure you do that. F prime of 0 is going to be the most straightforward, right? So we've got f prime of 0. We've got 0. I'm plugging it into the first derivative function. I get 0 minus 0 plus 9 equals 9. Therefore, this is positive, right? So at 0, we got a positive on this side. And that matches our graph. Okay? But if so I don't just want you to look at a graph. I want you to be able to do the math on this. So doing this part's a critical part of the situation also. Not just, you can look at the graph and tell, that helps. But I want to ask you to actually do the calculations. So the slope at 2, I'm going to plug this into the factored form. I think that, well, it's not, because it's such low numbers, it's not going to be a super challenge. But I'm going to plug it in here just to see this. And excuse me, I said I was going to plug it in, and then I didn't plug it in. So I plug in 2 and both of those spots, 2 minus 1 and 2 minus 3. So I end up with 3 times 1 minus 1, which is minus 3, which is a minus here in between, right? So at 2, I've got a negative slope. And it's coming down like this. That confirms that. And let's just finish them off. At 4, I'm going to go ahead with plugging it into, again, I'll use the factored form, 4 minus 1, 4 minus 3. And notice they're all positive this time. You don't have to have the exact numbers, but notice these numbers are small enough that I can just do this. If it's a bulky number, then the main goal is to just check the signs as the goal. So we end up with 9. That ends up positive again. So we end up with at 4, we get a positive as well. So it's going in this direction. So the question was, we were trying to determine local extrema, whether it was a max or a min. So on the left side of the critical point 1, we have a positive slope. On the right side, we've got a negative slope. Therefore, we've got a local max. Okay, there. And on this side, if we're looking at 3 now, we're looking over here, we've got to the left, it's negative slope, and to the right, it's positive slope. So we're at the bottom. So down here, we've got a local min. So one other thing you probably are typically asked for, and it's valuable when you're doing the function, is what is that minimum value? So you need the value of the function. What is the maximum value of the function? So we're also going to need to find f of 1 and f of 3. I mean, f of 4. Yeah, f of 1 and f of 3. So at f of 1, we end up with, what do we have? I'm going back to the original function here. So I've got 1 cubed minus 6 plus 9 plus 30. 1 is incredibly friendly. We got 10 minus 6 is equal to 4. 4 plus 30 is 34. So the local max is at 134. And the local min, we've got, and I'll put it here, put the answers together, but I'll do the local min calculation down here, and that's going to be at f of 3. And that is equal to 3 cubed minus 6 3 squared plus 9 times 3 plus 30. That gives us 27 minus 9 times 6 is minus 54 plus 27 plus 30. The 27s add to 54, so we end up with 0 plus 30. And therefore, the local min is at 330. All right? So again, we've got the goal was to find the local extrema, and we got the local max and the local min in that situation, okay? Now, let's continue on. And, the logic of it is the whole picture is what you need to get. What does the curve look like? Where is it increasing, decreasing? And all that information is valid, and make sure you answer the question. If it's asking for what are the local extrema, the local max occurs at 134, and the local min occurs at 330, right? So now let's go to the second derivative. I'm going to bring this first derivative down here, just so we have it nearby. And we're going to take the second derivative. And again, the second derivative was talking about plugging in the critical numbers, the critical numbers that we got from the first derivative test that allowed us to do when we took the first derivative and set it equal to 0. So now let's take the second derivative, and we get 6x minus 12. That factors out to 6x minus 2. All right? So our main idea here is to recognize that the second derivative then is equal to 6x minus 2. We need to plug in the two critical values, and the whole goal there is to use the instructions that use the second derivative test to determine the local extrema. And the idea is that if we plug in f double prime at the critical, plug in the critical number, okay, plug in 1, then we get 6 times 1 minus 12, which is 6 minus 12, which is minus 6, which is negative, which is consistent with what we had before. And it's the idea, if it's negative, then that means it's concave down and it's a local max. That's consistent with what we had before. And then a second derivative at 3, the critical number 3, critical value 3, is 6 times 3 minus 12. That's equal to 18 minus 12, which is 6, which is positive, which is concave up, which means we've got a local min. Okay? So again, we get the same results. Local max, and you'd have to plug it back into the original function to get the value, but the local max occurs at 134, and local min occurs at 330. Okay? That's finding the first derivative. Notice what the inflection point, okay? Notice this, the second derivative, one of the situations there was that where is this thing equal to 0? And if we set this equal to 0, it's where it's equal to 0 is it's possible to be, it could be an inflection point. It's not always. And we can talk about that situation in just a minute, but notice what we've got here. We've got this, set this equal to 0, x minus 2 equals 0, x equals 2. And you would find that x equals 2 is halfway. And the thing you would need to do to actually check it out, if you were just given the point blank question, where is the inflection point, set it equal to 0, solve, then you check to the left and you check to the right of it. Does the concavity change? Remember the definition of inflection point of inflection is that the concavity has to change if you're to the left and to the right of it. So in our case right here, you go to the 2, that's where the 0 could happen. While you look to the left, we get 1. And you plug it into the second derivative and you get a negative. You plug in the 3, you get a positive, which means it's concave up. Change of concavity at x equals 2, therefore it is a point of inflection. Point of inflection. And what is the y value there? Well, just give me a second. So f of 2 is equal to 2 cubed minus 6(2) squared plus 9(2) plus 30, right? That equals 8, 4 times minus 24, 4 times minus 6, and then we got plus 18 plus 30. That gives us negative 16, positive 2 equals 32. And does that match our situation? It's halfway between. And it's not always going to be the case that it's exactly halfway, the y value is, but it's halfway between. Notice it's halfway between 30 and 34 also. So when it's a nice polynomial, it turns out to be exactly halfway between the y values too. All right, point of inflection was there. All right, so if you've got questions on that, make sure you get with me, do some practice problems and get the information from it. And that's it. I'll get this recording up and you'll be able to view this multiple times. Be well.